Hello, so we're going to be doing this vodcast today of this handout that you guys have on linear combination of cosine and sine. And the first thing I want to talk to you about is what linear combination means. It's really just a general term for saying that whenever I have a constant times one thing plus a constant times something else. So like a linear combination of r and t might be like 3r plus 7t, or another linear combination of r and t would be like negative 2r minus 8t, right? Those are two examples of linear combinations of r and t. So what we're talking about here is a linear combination of cosine and sine. So some constant times cosine plus some constant times sine. So we see an example of a linear combination of sine and cosine right here in this function 3 cosine theta plus 4 sine theta. So what we're going to try to do is write this as one single thing, and it kind of gives us this heads up that what we're going to try to write it as is as a cosine with a phase displacement. In other words, that this is an example of a graph that is just a single cosine graph when we're just writing it in a different way. So let's try and figure out why that is the way that it is and how it works. So if I take a look at number one here, it says this graph shows y1 equals 3 cosine theta and y2 equals 4 sine theta. Which graph is which? Well, think about that. Make your decision. Okay, I think that the cosine graph is the one that is solid because it is the one that starts at its maximum. And I think that the sine graph is the other one because it has to be the other one, but also because it starts at 0 like sine graphs do. So what I want to do now is I want to look at number 2. It wants me to plot this graph. So I'm going to do this on my calculator and see what happens. I actually have this loaded in already. I'm in degree mode and I set my window to be the same as the window for this graph over here. So if I take a look at this, right, this is what the graph looks like. So you can see that I have the cosine graph here, and then the sine graph here, and then there's a third graph here that looks like it has an even greater amplitude than either of those two graphs, right? And it doesn't seem to be like it has it's neither at 0 or at a maximum or minimum here at 0. It's at some random value here. So I'm going to go ahead and try and sketch this on. I have a grid on here to make it a little bit easier. It looks like at x equals 0, it's right at 3. So I'm going to go ahead and graph that on here. And then at some point, a little bit more than a grid, one of these tick marks in, it reaches its maximum, which looks like it's about at 5. And then over here at about 1, 2, 3, 4, 5 tick marks, it seems like it's at back at the origin. And then, or the on the x-axis rather, and then after another 1, 2, 3, maybe 3.5 tick marks, it seems like it's at the bottom. And then back up here after 2 tick marks past 180. Okay, or past, I lied when I said 2 tick marks past 180, right about here. Okay, so now I have this graph on here. Okay, and it appears that this graph is just a sinusoid, right? So if I think about it, I'm going to go ahead and turn the original two plots off so we can see this one a little bit more clearly, right? This is just a regular old sinusoid, and if I forget where the equation came from that I wrote it down, I could figure out the equation for this graph just by thinking about the four things, right? What is its amplitude? What's its sinusoidal axis? What's its phase displacement? What's its period? So if I look at this, let's start with the things that are not particularly different, right? So sinusoidal axis is clearly here at y equals 0, right? So there's no sinusoidal axis that's not 0. If I look at the period of this graph, each tick mark here is 30 degrees. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Tick marks 12 times 30 degrees is 360. So it still has a period of 360, which is my normal period. But its amplitude is not 1, and its phase displacement is certainly something random. So I can be pretty sure, if I knew what the coordinate of this point was here at the maximum, then I would know both the amplitude and the phase displacement. So let's go ahead and use our calculator to figure out exactly what that point at the peak is. There's a second calc maximum value, just like there's a second calc intersection. It's really pretty handy. So the way that it works is you move the little flashy thing to the left-hand side of the peak, right, where it says left bound. You press enter. Doesn't matter exactly where you are, as long as you're the left of the peak. And then right bound, you move to the right of the peak and press enter. And then you go to your guess and you press enter. It thinks about it for a while and tells me, okay, this peak happens exactly at y equals 5 and x equals 53.13. Okay, so what I want you to do now is if we look at question number 3, it says find the amplitude A and the phase displacement D using the maximum feature of your graph. Go ahead and pause this, write down what you think the answer is for A and D, and then come back. Did you pause it? Really? Go do it. No, really. Pause it. Okay, so I think the amplitude is 5, and I think that the phase displacement is 53.13 degrees, right? Because that's telling me the x value at which this maximum occurs, which is the phase displacement for cosine. So that tells me that the equation for this is going to be y equals 5 cosine theta minus 53.13 degrees. So number 4 here says plot that and make sure that it actually is the same graph. So let's do that. Okay, 5 cosine x minus 53.13. And you know what, just to make sure that I can tell what's going on, I'm going to make that one bold, right? So I can see that it actually lays on top. It totally does lay on top. So that's perfect. This is exactly my angle. So yes. Good. Okay, so we observed that this equation works just by graphing it and seeing what happened. Now, what we're going to do is try to think about, well, okay, if I didn't want to do it graphically and figure out what the equation was from the graph, how could I figure out what the equation was algebraically? And really the key relies in this picture here, which is kind of weird where it comes from, but just roll with it. So what I did is I made a picture in the UV plane, right, that had the u coordinate was the coefficient of the cosine part of the coefficient of the cosine part of the linear combination, right? And then the v coordinate here, this is the sine coefficient. Okay, this is easy to remember because u is cosine, v is sine. It's the same thing here. So what we're doing is we're just going to observe that some interesting things about this triangle give us the important things that we need in order to write this equation the way that we wrote it from the graph. So let's think about the Pythagorean theorem here, right? How long is the third side of this triangle? Well, it's just a 3, 4, 5 triangle. So this side is 5. Huh, that seemed to be my amplitude. That's convenient. How big is this angle here? Well, what I want to do is I want to use 4 and 3, the sides that I knew to begin with, not 5, the one that I calculated. So I would say that tangent of theta, or tangent of d, excuse me, is v over u, which is 4 over 3. So d is equal to, it says here, arctangent 4/3. And I'll talk more about why it's arctangent 4/3. Because after all, right, we only have one angle here as our phase displacement. I don't have an infinite number of angles. The problem is it's not always one of the angles in the principal branch of tangent that is the one that we want. So we say arctangent so that we consider options outside of the principal branch if necessary. Okay, but here D, look at my picture, right? D is in the first quadrant. That's in the principal branch of tangent. So if I do, let's one more time. Okay, so if I do inverse tangent of 4/3, oh, I get 53.13 degrees, right? Which is, in fact, the phase displacement that I figured out from my graph. So it looks like this triangle is giving me everything that I need in order to figure out the equation of my cosine, that is my one cosine that is a linear combination. So let's look at another problem and see how it extends to different sorts of problems. Okay, so we're going to go ahead and look at problem 7 next. So we're going to express, instead of the linear combination we had before, now we're going to work with this one. Y equals negative 12 cosine theta plus 5 sine theta. So what the worksheet did for you is it drew in the UV plane a diagram that was a lot like the diagram that we just had. The u coordinate was the coefficient of cosine, which in this case is negative 12, so it's going to the left, right? And then the v coordinate here is the coefficient of sine. It's positive 5, so it goes up, okay? So if I look at this in the UV plane, the angle in standard position for this triangle is D, the phase displacement that we're looking for, and A is still the amplitude. So let's use the Pythagorean theorem to figure out what the amplitude of this is. So I know that A squared is going to be equal to 5 squared plus negative 12 squared, which you may actually know this is a Pythagorean triple, but let's go ahead and do it on our calculator just in case. 5 squared plus negative 12 squared is equal to 169. Square root of that is 13. So this is equal to 13. So that's my amplitude. Now, if I want to find d, right, I know that the tangent of d is v over u, right? So it's 5 over negative 12. So, but I want to find this particular d angle here, right? I don't want a different value of d because I know that the coefficient of cosine is negative and the coefficient of v is positive. That puts me in the second quadrant. If I do d, and I try to do this on my calculator using inverse tangent, look at what happens, right? I get inverse tangent of 5 over negative 12, and you get negative 22.62 degrees. D is obviously not negative 22.62 degrees. Where is negative 22.62 degrees? Well, it is the angle associated with this triangle over here, right? That has plus 12 and minus 5, right? Because negative 5 divided by 12 is the same thing as 5 divided by negative 12. So it's giving me this angle here. But what I actually want is D is marked there, which is just 180 degrees more because this is a straight line here and there's 180 degrees in a straight line. So if I add 180 to this, plus 180, I get 157.4 degrees, which is D. And then I can use those two pieces together to write the general equation, y equals 13 cosine theta minus 157.4 degrees. Now, it's always going to be a cosine graph because when we originally did this, we looked for the phase displacement that was the maximum of the curve, not the critical point for sine, which is at the middle of the curve. So we can talk more about where this comes from later once we know a little bit more about the different properties. But for now, I think this is really just about execution. So I'm not going to go through number 8 and 9. We've been at this for 12 minutes. So what I want you to do before you come to class tomorrow is try 8 and 9 on your own. And we're going to check that at the beginning of class. Have a good night. See you tomorrow.